Okay, everybody, this is September 28th, asynchronous assignment, and it's about R squared, a little bit about computer output, and then unusual points. This is sort of kind of tying up last little pieces of information for this chapter. Um, Before we go on to, for linear models, before we talk a little bit about nonlinear models. So we'll start out explaining what R squared is. R squared, the name for R squared is coefficient of determination. It is different than correlation. There's a super specific sentence that we use to interpret R squared. And for the intents and purposes of the AP test, you need to use this sentence for R squared. So R squared is the percent of variability in the Y variable that is explained by the straight line relationship with the X variable. We'll often leave this straight line part out, but this sentence, you'll pretty much have this cookie cutter frame of a sentence, and this is how you will interpret R squared when you're asked in context. What R squared is mathematically, when we take one and then we minus basically the sum of these ratios. We square the residuals on the top of this fraction, and we square basically the deviations of the y on the bottom. And the smaller my error, the smaller my residuals, the closer R squared is to 1. It basically takes into account that part of the variation is explained by whatever my x is, and that there are some other factors out there that are also causing the y to change. A little bit about computer output. So this is from a computer program called Minitab. It's like a professional statistical software package, and it's good for you guys to be able to pick out information even when it's presented to you in different formats. There's many different computer programs out there. This is one of them, and part of it is confusing, but hopefully if you get more comfortable with it, then you can see it. This type of computer analysis can also look for multiple variables. It's made for pretty complex statistical analysis. But up top, it should look like you can understand the regression equation. That exam score, that's my y variable, my dependent variable, equals 44.5 plus 0.55 of the revision time. And it's basically saying that my y-intercept for this is 44.5, or the expected exam score, if there's 0 revision time, is 44.5. It's a pretty low score, so I might want to spend some time revising. And that for each unit of revision time, the predicted exam score is increasing 0.555. Down here, I can see basically that the constant, that's the y-intercept. And in terms of mathematics, you can see where this constant is all by itself. There's no variable. The next one here is the slope, because it is the coefficient of this variable revision time. And I mentioned that this program kind of leaves space for multiple variables. I could have other variables that might impact exam score. Revision time is one of them. It could be study time, could be another variable, or what are some other things that you could think about what might affect exam score? Whether it's the GPA in the class, current grade in the class, there's all kinds of things that impact the exam score. Revision time is one variable. And then down here, I can see the standard deviation of the residuals, meaning that I'm expecting to be off in my exam score prediction by about 6 points. So if I make a prediction for 20 minutes of revision time, and then I kind of know that, well, whatever I get, I'm most likely on average going to be off by about 6 points. And then here is that R squared. And what I would say to interpret this, I would say 72.8% of the variation in exam score is explained by revision time. So it's the percent of variability that revision time that explains of the exam score. That really means that there's 27.2% of variation that's explained by other factors other than just revision time. This right here, R squared adjusted, is a measure we don't use. These ones right up here, these are for a later in the class. Second semester, we'll get into using these, and we'll talk about what they mean. Some facts about R and R squared. They mean different things, but they are closely related. If you know R, you can square it to find R squared. So if I'm given the correlation coefficient, I can find R squared by squaring it. So correlation coefficient, coefficient of determination. If you know R squared, you can square root to find R. There's one kind of caveat: R squared is always positive, so it does not give direction. So I do need to know which direction it is, if it's positive or negative. R squared is always a percentage. R, however, is not. Okay, a little note about outliers. So when I am looking here, I have this data about knee versus ankle diameter. So I have this graph that ankle diameter used as a predictor for knee diameter. And up here, I notice this point that's kind of way above. So an outlier on a scatter plot is a point that does not follow the general pattern, right? Especially my line, it's very removed from that line. It's going to have a large residual, and it's removed in the y direction. So this is an outlier. It's an unusual point. That means that there is like this actual value, this actual knee diameter is much bigger than would be expected from all these other, these other ankle diameters. The outliers, they might have some influence on the line, the slope, and on the correlation coefficient, but it's hard to know without actually kind of playing around with the data, like calculating it with and calculating it without. They don't necessarily have a large influence. They can, but oftentimes they might not even do too much. An influential point is a point that is removed from the data in the x direction. So over here, there's this one point, and it's like way far away from all the other data points. And it this particular one actually follows kind of the pattern, that least squares regression line. That point is almost like right on it. What happens is an influential point, when it's removed in the x direction, it has a strong influence on the calculations, on the math, and it can alter the slope and the correlation significantly. So without this point, this data may have a correlation coefficient R equals 0.7, like moderate, maybe even 0.6. With that point, it could move the correlation up to like 0.9. So this one point can have significant influence. And the same thing if I have points kind of all together and then one point very far removed, it can swing the slope significantly towards it. So you just have to be very careful of these influential points, and sometimes calculating values with and without that influential point can be important. All right, that's it for today. Hopefully this was helpful, and I will see you all on next class period.